We'd like to take the function you see here, f of x is equal to 2 times x squared minus 9 in the numerator, divided by x squared minus 4 in the denominator, and apply pretty much just about, every algebraic and calculus technique that we have so far to learn everything that we can about the graph of this function. We're going to start by considering the intercepts. So we'll start with some algebra here. This thing is going to have x-intercepts whenever it is equal to 0, and in this case, since it's a fraction, whenever its numerator is equal to 0. So we're going to consider 0 is equal to x squared minus 9. That's the same thing as x squared is equal to 9, and that says that x is equal to plus or minus 3. So we have two x-intercepts. We're going to have one at negative 3, 0, and we're going to have one at positive 3, 0. The y-intercept will be what happens when we plug 0 in for x. So in this case, f of 0 is going to equal to 2 times negative 9 divided by negative 4. And if you simplify that, you'll get 9 halves. So we'll have a y-intercept at the point 0 and 9 halves. We can also look for things like vertical asymptotes. Right? Vertical asymptotes are going to occur when the bottom is 0 but the top isn't. And in this case, it looks like those are going to happen when x is plus or minus 2. So we're going to pick up two vertical asymptotes. X is equal to negative 2 and x is equal to positive 2. We can see that the bottom is 0 at each of those values and the top isn't. The top will be something else. If we rewrite the function for a moment as f of x is equal to 2x squared minus 18 divided by x squared minus 4, we can note that the top and the bottom have exactly the same degree. So if we can consider limits as x approaches infinity or as x approaches negative infinity, we will discover that we have a horizontal asymptote at the value that is the ratio of the two leading coefficients, so 2 over 1 or 2. So vertical asymptotes, horizontal asymptote, we have x-intercepts, we have a y-intercept. It's a fair bit of information that we're getting just from our algebra and then a little bit of limits that we have here. Now we can keep going and start to consider what happens with the first derivative. The first derivative will allow us to determine where the function is increasing or decreasing, and we can also use that information to determine where we have relative extrema, if any. So f prime of x is going to be equal to, and I'm going to put a little check mark here by f of x. I'm going to use this version of f of x, 2x squared minus 18 over x squared minus 4, because it's going to be a little bit easier for taking the derivative. So the derivative of the top is 4x. We multiply by the bottom, which is x squared minus 4, minus the derivative of the bottom is 2x. We multiply by the top, which is 2x squared minus 18, and we divide all of that by the bottom squared. So x squared minus 4 squared. That says the first derivative is equal to 4x to the third minus 16x minus 4x to the third plus 36x, all divided by x squared minus 4 squared. And if we simplify that up a little bit more, the x to the thirds are going to add to 0, they disappear. The negative 16x and the 36x will be 20x, all over x squared minus 4 squared. So when we look at this and consider the top, we're going to find that we have a critical number at x equal to 0. This thing also is undefined when x is plus or minus 2, but we've already discovered those numbers. They're not in the domain, so we'll ignore them as critical numbers, but we'll remember that they show up as vertical asymptotes. So if we create a sign chart, our sign chart, we're going to need to consider negative 2. We're going to need to consider 0. And we're going to need to consider positive 2. And we'll look at the first derivative at a test value in each one of these intervals. So I will choose negative 3, negative 1, positive 1, and 3. I'm going to note that in the denominator of my first derivative, whatever value I get, I'm going to square it. So that's always going to be positive. So the sign's going to come entirely from the numerator. So f prime of negative 3 I expect to be negative. F prime of negative 1 I expect to be negative. F prime of positive 1 is plus. F prime of 3 is also plus. So we're decreasing, decreasing, increasing, and increasing. So this function is increasing on the intervals 0 to 2 and from 2 to infinity. It is decreasing on the intervals negative infinity to negative 2 and negative 2 to 0. And it looks like we should have a relative minimum at the point 0 and 9/2, that is at our y-intercept. 0 is in the domain of the original function. We've already found the value for the y-intercept, and we see a change in increasing, decreasing behavior in this case from decreasing to increasing, which implies a relative minimum. So we're starting to collect an awful lot of information here. We can go one step further and we can see what we can also learn from the second derivative. So let's remember that the first derivative was 20x over x squared minus 4 squared, and see what we can do with that on a new page. So I'm going to write that f prime of x was equal to 20x divided by x squared minus 4 squared. And I'm going to take the second derivative. So f double prime of x is going to be equal to 20 times x squared minus 4 squared minus 2 times x squared minus 4 to the first power times 2x, that's all from the chain rule, and then times 20x. That's all going to be over x squared minus 4 squared squared, which is x squared minus 4 to the fourth power. So I'm going to reduce some powers here. We have x squared minus 4's everywhere. We have one that I can cancel here. I can cancel one of those here, and I can cancel one of them here. Then I'll see if I can't clean things up a little bit. I'm going to have 20 x squared minus 80. Then I'm going to have minus 80 x squared, and that's all going to be divided by x squared minus 4 cubed. A little bit more cleanup, and we get negative 60. My pen does not want to write very well right now. Negative 60x squared minus 80 divided by x squared minus 4 to the third power. And if we factor out, let's say, a negative 20, we'll have negative 20 times 3x squared. Oops. Plus 4. That's all divided by x squared minus 4 cubed. So when we look at this and try to find out when it can be 0 and undefined, it'll be undefined at plus or minus 2. Well, we've already seen the first derivative wasn't defined there, and the function itself wasn't defined there, so nothing new. We've picked those up as vertical asymptotes. When we look at the top, the only thing that could potentially be 0 is what we see in the parentheses, but 3x squared plus 4 is going to have to always be positive. The 4 is positive, the 3 is positive, and anything we square, the worst it can be is 0. So the smallest that expression could potentially be is 4. So we're not going to find any critical numbers in the domain of the function here. So even though we don't find any critical numbers or potential points of inflection for the second derivative here, we still need to consider what happens at negative 2 and positive 2 at those vertical asymptotes. So we can still create a sign chart. We'll use negative 2 and positive 2, and we can still consider concavity in each one of the resulting intervals. So let's test at negative 3, let's test at 0, and let's test at positive 3. So when we have negative 3, we've already said the top in parentheses is always going to be positive, is going to be multiplied by a negative, so the top is always going to be negative. So what we're really interested in is the bottom here. So if we take negative 3 and square it, we're going to get 9 minus 4 is 5. 5 to the third power is positive. This should be negative. We should be concave down here. When I plug in 0, 0 squared minus 4, that's going to give me a negative. To the third power, still negative. Since we have a negative in the top as well, this is going to be positive, concave up. And when we plug 3 in, we're going to get a result almost exactly the same, actually exactly the same as we did for negative 3, because when we square 3, and when we squared negative 3, we get 9 in both cases. This will once again be negative, will be concave down. So this function is concave downward on negative infinity to negative 2 and on positive 2 to positive infinity. It is concave upward on negative 2 to 2. Now in the next video we'll take a look at how we can take all the information we've discovered, organize it into a nice table, and then use that table to begin to graph the function based on this information, that is to sketch the curve.